Hello everyone. Today I will present our paper Improvement of Emergency Communication System using drones in 5G and beyond for safety applications. I will conclude my presentation by talking about introduction, our contribution, meta-heuristic optimization algorithms, performance analysis, and conclusions. UAVs, often referred to as drones, have garnered attention in recent time owing to their versatility, independence, and wide range of applicable industries. Indeed, a multitude of applications, including those in telecommunication, military monitoring and surveillance, search and rescue operations, medical supply delivery, and disaster management, have been seen as being significantly facilitated by drones. Rearranging the network in the event of complex issue that arises in communication system after natural catastrophes such earthquakes and floods takes a lot of time, and the most important thing is to keep people safe. In a situation like this, swift and effective search and rescue operations are desperately required. Natural intelligence or artificial intelligence algorithms have been widely used as search and optimization techniques in variety of fields lately, including science, engineering, and business. The process of determining the best course of action under certain restriction of for a given goal or object is known as optimization. Science have proposed a novel idea that has been validated via optimization. Our contributions are that drone-assisted emergency communication system in disaster is presented where clustering is used, and the performance of proposed system is improved through two meta-heuristic algorithms, CUCO and PSO algorithms. The cluster size is optimized by the algorithms, and Markov chain model is used for an analytical investigation. And lastly, the analytical analyses are backed up by the simulation results, which are also presented. Simulation shows the improvement in terms throughput and package dropping rates. CUCO search algorithm. Herd intelligence is the primary focus of the CUCO algorithm. Drones are shown functionally in the ad hoc networks. The goal of the CUCO algorithms is to allow drones to communicate with one another socially. The search terminates after the genetic algorithm has finished the requirement number of generations. Each cluster size optimizes its size based on the historical data to achieve optimal performance. It's the best position drones on in ad hoc networks that the CUCO algorithms primarily focus on estimating. Drones in a herd with a randomly determined cluster size will improve their position relative to previous iteration until the object is met. In a sense, the following phases make up the algorithm. An arbitrary beginning cluster size is used to form a starting swarm. All drone values are exchanged inside finets. Each drone has a local best of current generation. There are many bests in a pack as there are drones. In modern ad hoc networks, the global best is derived from the local best. And position, cluster size values, and these are random generated numbers. The value of internal weights and the scaling factors. Particle swarm optimization. A PSO is essentially a herd intelligence-based algorithm. Finite operating drones have been seen. The PSO algorithm relies on drones exchanging social information with one another. The genetic algorithm's generation count determines the search strategy. Using the prior expertise, each CS modifies, cluster size modifies its position to find the optimal spot on the course. The PSO method is primarily focused on approximating drones' position inside finets to drones that have the best finite positions. The condition in which this approach cluster size occurs in arbitrarity, and often drones in the herd are in a better position than they were in their prior moves. This process is repeated until the goal is obtained. The following phases make up the algorithm in its entirety. A startup herd is created with random choosing starting cluster size. All of finite drones' conformance values are computed. The local best of the current generation is assigned to each other drone. The number of drones is equivalent to the number of the best in the herd. In the current finite, the local best are used to choose the global best. Cluster size has been updated, and then position, cluster size values, and random values are numbers that are generated randomly. And W is the internal white value, and the Z1 and Z2 are scaling factors. Because UAVs can move in three-dimensional, obstacle in their route may be easily avoided. For the length of the time t, it's expected that the height h will not change. X of t, y of t, and h is the location of the UAV represented in terms of time varying x and y coordinates. The exact position of the UAV are determined by the launch and recovery sites, often known as pre- and post-mission locations. The symbol d will represent the distance between starting and destination point. The one way of to express the minimal distance between beginning and destination point is as follows in the first equation. There must be one cluster head per cluster. There are NCL number of cluster heads. As a consequence, the average count of cluster members inside a cluster may be expressed in the second equation. The length of a package transmission with a collision and the period of the slow and interval of a successful package transmission, all of them are given in the last equations. The normalized system throughput, which is determined by dividing the average length of the transmit payload by the average load time. The first two equations is about the system throughput. With the first two equations, you can get the throughput easily. And the last equation is about the package throughput rate. When a transmission attempt fails, a package will be discarded after a maximum number of retransmissions. Therefore, the PDR can be calculated in the last equation. This section assesses the effects of various meta-heuristic optimization strategies in FANETs, and a comparative analysis is provided between suggested system and meta-heuristic optimization techniques. With MATLAB, the simulation results are achieved, and the table provides parameter values used in the simulation. On the left side figure shows the throughput for 50 drones with a cluster size of 5. As the number of drones increases, throughput increases up to a certain point, beyond which it decreases further as more packages compete for same channel and more collisions occur. Meta-heuristic algorithms methods always have throughput that exceeds that of proposed system. When there are fewer drones, the Kuko search algorithm outperforms for the PSO algorithms in terms of throughput. PSO algorithm throughput is greater than Kuko algorithm when the number of drones is large. Compared to suggested system, meta-heuristic algorithm techniques are more efficient, as is seen from the figure, left side figure. On the right side figure, the PDR versus the total number of drones is shown. After the allocated number of attempts, a package will be destroyed in the event that the transmission attempt is unsuccessful. Kuko algorithm has a lower PDR than the PSO algorithm, when there are fewer drones present. A higher drone count results in a lower PDR for PSO algorithm. The PDR of the meta-heuristic algorithm techniques is consistently less than that of the suggested system. Consequently, it's evident that meta-heuristic algorithm techniques enhance communication efficiency by increasing throughput and lowering PDR. In this study, we optimize cluster size in finite using meta-heuristic optimization techniques to get the best throughput performance. To establish the link between parameters, an analytical research based on Markov chain is drawn, and the results of the simulation are shown. A comparison is shown between PSO and Cuckoo search algorithms, and it's clear that meta-heuristic algorithm techniques improve communication reliability and efficiency. The throughput is highest for the PSO algorithm when the number of drones is greater than 25. The PDR is also lowest for PSO algorithm until the number of drones is 45. It's apparent that PSO algorithm can be a better algorithm in this paper. The Scientific and Technological Research Council of Turkey, TÜBİTAK, is funding this work through Project 123E106. Thank you for listening to us.